Hello, people of physics. Today we are going to do a problem called the box on a box. It's a really easy problem. You have a box that is on top of a box. Those boxes are moving together, and there's only a force that's applied to one of them. So in this first case, you got some tension that's pulling on the bottom block or box or whatever, and you'll normally see this phrase, they stick/slide together on a frictionless table. So that tells you that there is friction between these two blocks. Say yes, friction, because they're stuck together. But there is not friction between the bottom block and the table. Kind of like an important idea. Okay, I'm going to give you some numbers for this one. So let's say the problem told you that the tension was, I don't know, how about 10 newtons? And the mass of the first block is 2 kilograms. And the mass of the second block is 4 kilograms. What we're going to be trying to figure out is the force of friction that is between the two blocks. Okay, so to do that, I'm going to draw a free body diagram. And for the blocks A and B, you should have these following free body diagrams. So for A, I would have a normal force up, which I'll call NA, and then a weight force down, which I'll call MAG. Then I'll have a friction force going forward. Now that's kind of weird, but if you think about it, if there was no friction between the two blocks, then when the B block moves underneath of the A block, there would, nothing would happen. It would just stay still and not be pushed in any direction. Okay, then for the B block, there's actually some weird forces here. You would have the weight force down, we'll call it MBG. But then you would also have the action-reaction of this normal force right here. So what this normal force gives you, call it NA. I might call that actually NAB because it's between block A and block B. Okay, and then I would have another normal force that goes up. And let's say I'll call this NB, and I might even put like a C on it and pretend like, okay, well the ground itself is like a giant block that I can call block C. But let's not do that. Basically, I mean, if you wanted to put numbers to it, it's really simple. You know that the weight of block A is going to be 20 newtons, and so the normal force is 20 newtons. Okay, so, well, then what that means is that this normal force is 20 newtons, and then this weight right here, MBG, would be 4 kilograms times 10 meters per second squared, so 40 newtons, which would mean that this normal force supporting the bottom block B is 60 newtons. That might make it a bit more obvious for you. It's just trying to say that the ground has to support both block A and block B, so their weights combined, which is the 40 and the 20. If you can just kind of see that without having to write normal force as this action-reaction pair, that's totally fine. We'll use this later when we have to use normal forces to find friction, but for right now you don't know how to do that, so this is just kind of an exercise in making sure you can do the weight and the normal forces. Let's get to the forces that actually matter for this problem, though. That tension would be applied to B, to the right, and the frictional force would actually go backwards, F. And these are a force pair. They're an action-reaction pair. So the bottom block is kind of like pulled forward by, actually the top block is pulled forward by the bottom block, but that bottom block is resisted a little bit by the top block. Okay, so if I was going to write equations of net force for block A, I would just have friction. For block B, I would have T minus friction. Now, for this problem, to figure out what the amount of friction is, all I really need to do is figure out what the acceleration of the system is, and then use that with one of the masses of the blocks to kind of work backwards and figure out what friction needs to be. So if you remember, the trick with systems is even though you have objects that are separated, you can sort of treat them as one object, which I haven't really talked about it too well in the videos, but it's like I'm adding together these two systems of equations, and then the frictional force is canceling, and what I'm left with is the net force A plus the net force of B is equal to the tension, which is basically just trying to say the net force equals tension in this problem. Again, this would be different if there was friction on the ground, but there isn't. And the reason why I would want to do this is because I can figure out what the acceleration is by pretending that the two blocks are one and I have a combined mass of 6 kilograms. So I'm just going to go ahead and erase some of this work that I just did, and I'm going to find that acceleration. Okay, so to find the acceleration of the whole system, I would do the net force on the whole system and divide that by the mass of the total system. In this case, the net force is going to be just that 10 newtons because there's no friction on the bottom block. And then the mass is 2 plus force of 6 kilograms. So we're looking at like 1 2/3 or 1.6 repeating meters per second squared is the acceleration. Okay, so maybe you already see the way that I can figure out what the force of friction is I would find the net force of A by doing the mass of A times that acceleration. So 2 kilograms times 1.6 repeating meters per second squared is going to give me, 3 1/3. So we'll say 3.3 repeating, which, I'm sorry, not meters per second squared, kilograms, meters per second squared, or newtons, which is the force of friction, because you now know that the force of friction is the net force, so 33.3 newtons. Okay, now I can verify this by taking a look at the net force on B, if I want to. You really don't have to do this, but I'm going to go ahead and do it anyway. Multiply the mass of B, which is 4 kilograms, times that acceleration of 1.6. So 4 times 2/3 is what? Oh yeah, 6 repeating newtons. Okay, so that's the net force on B, and that makes sense because if I wanted to take 10 newtons of that tension and then subtract the 3 1/3 newtons of friction, what I would be left with is a net of 6.66 repeating newtons. Yay, physics works. Okay, so that's how you find the force of friction between the two blocks. Let's do another problem. This time, we are going to take a look at two blocks that are stuck together, and they're sliding on a frictionless table, but now you're pushing the top block. So this is like almost like a Jenga kind of move. You're pushing the top block, you don't want to move the bottom, or you are moving the bottom block, and they're like all sliding together. Okay, so in this scenario, I'm going to give you numbers and say that the force applied to the top is, let's make it fancy, 80 newtons. The block A is going to be 1 kilogram, and block B, let's make 4 kilograms. Okay, so if I drew free body diagrams for each thing, I'll do A first. You would have the exact same thing for the weights and the normal forces. It's kind of weird, but I'm going to go through it again because you'll have to do this later. Let's start with, we'll start with A, the bottom one. Wait, no, we did it the other way around last time, so we'll do that same thing this time. Okay, so we've got the weight, mb times g, of the top block, and then there will be a normal force, which I'll call nba, because it's between block A and B, which, again, it's kind of like saying, and as much as this B block is supported up with nba, block A is pushed down, and these forces are both normal to the surface interactions. That's why it's called, a normal force. But anyway, I'll draw that normal force down here in BA. Again, if I want to give numbers to it, because that might make it a little bit easier to understand, 4 kilograms times 10, so this is 40 newtons. So the normal force is 40 newtons, which means 40 newtons is also pushing down on block A. Okay, then there's also the weight of block A, which would be a little bit smaller, so I'll draw it smaller. scale ma times g, which again would be 1 times 10, so 10 newtons. And then there would be a combined normal force to support both of those, which I would call ma NAC, which is kind of a weird thing. I'm just pretending that the ground is another box that we're calling C. And boxes on boxes. Maybe it's all in an elevator and you're crying. I don't know. Anyway, this would just be 50 newtons. And again, you're going to use this information later when we talk about how the normal force affects friction. For now, it's just good practice. Okay, so now let's talk about that F, the external force. The external force only acts on the top block. So I would need to put that external force here. Again, there is a force that pushes the top block, but not the bottom block. Okay. Well, in order for these two to stick together, there has to be friction between them. So there is, yes, friction. Yes, friction here. Which would mean that this is kind of a weird idea, but there's friction acting back on block B. But that same force of friction is actually what pushes block A forward. So I would make sure to draw that friction on both blocks and make sure that I notice that they are congruent. Okay, then if I look at block A, I'm actually done. I don't need to include friction between it and the ground because in these problems there is no friction between that block and the ground. All right, so this lets me write equations of net force. The equation for net force on A is just friction. The equation for net force on B is F minus friction. Okay, and again, I need to find the net force on A by taking the mass of A times the acceleration. Same thing with the net force on B, mass of B times that shared acceleration. And if you haven't guessed, the way that you find the acceleration is by treating the whole block as a system. And again, in this idea of the systems, it's like these two frictional forces cancel out. It's like I try to add the two, friction cancels out, and I'm left with the net force of A plus the net force of B is just that force of friction, which is like saying the net force of the whole thing is friction. Again, you don't have to write that out to see it. If you just understand that you can use the equation A equals sigma F over M for the entire problem, like all of the objects combined as one big object, then just do that. That's fine. So to do this, I would take my net force is 80 newtons, and then I divide that by a mass of 5 kilograms, which is an easy number, but I can't think of it. 80 divided into 5 parts is 16. Yeah, 16. Okay, so 16 meters per second squared is the acceleration of both blocks. So if I want to find the net force on A, then I would take 1 kilogram, multiply it by 16 meters a second squared, 16 newtons. Wow, tons of math. And so I now have just figured out that the force of friction is 16 newtons because that is the only force that's acting on the bottom block A. If I want to verify this, I can look at block B and write an equation of F minus friction. So this would be 80 newtons minus 16 newtons, which is, oh God, what, 64? And if I want to find the net force to check it, I can say 4 kilograms times 16 meters per second squared, which would give me, oh my God, 64 newtons. Okay, anyway, you're just using this part to check. It's not that big of a deal to find the force of friction between them. You found it. It's 16 newtons because it's the net force, the only thing acting on it. Okay, so you're going to have a couple of these problems on a little practice assignment that you're taking. Good luck, and if you made it all the way to the end of this video, I'm so sorry, but I have no cat or child around me, so I am sad and alone, but you are done with this video.